Hello everyone, welcome back to another episode of Simple Harmonic Motion. We are in episode 7 today, and as promised in the previous video, I'm going to do a video on how to sketch energy graphs for Simple Harmonic Motion, right? And that is what we're going to do today. But before we go on into how to draw energy graph, let's recap a little bit on what we learned in the past video because it will be useful eventually. So we learned how to sketch velocity against displacement graph, and we talked about some displacement of v with respect to x, and I also said I will derive this, right? Don't worry, I'll derive this in the next video. And actually turns out there's another way to derive it without using differential equation. My friend was talking to me in the past few days and he said that there's another way, a simpler way. Don't worry, I'll show both. I show differential equation and the other way as well. I won't tell what is the way is. You'll see in the next video, okay? And we talk about acceleration against displacement. And we talk a bit on energy, at where kinetic energy is 0, potential energy is maximum, and so on and so forth. So with that knowledge in mind, we're gonna sketch our graph. Okay. So before sketching our graph, I'm going to show you a simulation, and this simulation involves using pendulum instead. So all this while I've been using a spring to show the process of simple harmonic motion, but pendulum can also work in simple harmonic motion, and I'm going to show you the simulation now. So this is our pendulum here, so I'm going to swing my pendulum here. I want you to have a look at how this energy graph on my left hand side here works. Okay, I'm going to make it slow a bit. Okay, now at equilibrium. Remember at equilibrium we say our velocity is maximum. When velocity is maximum means our kinetic energy is also maximum. Realize your kinetic energy is maximum here. Your potential energy is 0. And since energy cannot be destroyed, your total energy should be constant. So that is why your KE, when there's no PE, your entire KE is equal to the total energy. Now let's continue. Okay, let's say at this point. You see, at this point, your KE plus PE becomes your total energy. Now at maximum, your PE is maximum and the KE will be 0 at the maximum amplitude. So therefore total energy is will be your PE. Realize the total energy bar is not fluctuating up or down. It's constant. This is what I mean by energy cannot be destroyed. Therefore total energy should be constant. When you add KE and PE, you should be constant. Alright, so I hope that simulation gives you an overview on how energy works, how it interchanges between potential energy and kinetic energy. They're basically really good friends in simple harmonic motion. And that was a pendulum simulation. It works the same way in spring as well. As long as it is simple harmonic motion, it looks like that. Okay, so now without further ado, let's draw our graph. Okay, so this is your graph. Remember to label your axis. Okay, it's very important. Energy and axis M. So we're going to start with kinetic energy. We're going to draw our kinetic energy graphs first. So as far as you're concerned, at the maximum amplitude, our kinetic energy is 0. I'm going to label my maximum amplitude here as A. I know in the previous video I labeled it as X0 for some reason. I have no idea why I label it as X0 because I'm used to labeling at A. But I think, yeah, it's the same thing actually. X0 is equals to amplitude. It's just whether you want to label your maximum amplitude as X0 or as an A. I'm going to use A in this video, okay? But don't get confused. It's the exact same thing. Okay, coming back. We know it is 0. So that is one of the 2 points we have. Then we know at equilibrium, in other words, at X equals to 0, your kinetic energy is maximum. So I'm going to put my maximum as here. So if you were to draw the graph, your graph will look something like this. Actually, that's a really nice graph. Okay. And I know if you have a thought or maybe a question about it, why we don't have a negative portion of this graph and there's a negative velocity here. Okay, that's actually a really good question. Because, okay, let's look at the equation. We know kinetic energy is equals to 1 over 2 mv square, right? So if we now put this negative inside this v and we square it, you will get a positive value. Regardless whether your velocity is positive or negative, mathematically, when you square it, you're going to get a positive value. That is why your energy graph has only the positive portion of it. Okay, now let's further derive this. So we know 1 over 2 m. We know in the previous video we have seen this equation, right? V equals to plus minus omega x naught square minus x square. So let's use this equation. Now we have v square here. So what happens if we square this? You're going to get omega square. Your square root will be gone because you're going to square it. I'm going to change my x naught to a, but it's the same thing, right? A square minus x square. This is what you'll get. So now let's open up the brackets. This is what you'll get. Oops, I think I forgot my omega square. Then got omega square x square. So remember to open up your brackets carefully. Okay, so if you realize, my beautiful, amazing friends, this is actually a constant. Why? Your mass is a constant. Your omega is constant because your period is constant unless you change probably the length of the spring or spring constant, or if it's a pendulum, the length of the pendulum that will alter the period, then your omega will not be constant. But generally, without doing any of it, your omega is constant because your period is constant, right? Your amplitude is constant as well. Your maximum value, maximum amplitude. So, this whole thing is constant. That is why your kinetic energy graph will give you a negative x square. In other words, a negative quadratic graph. And you did get a negative quadratic graph. It's pretty cool, right? How it relates to each other. Yeah. Now, let's have a maximum kinetic energy equation. So, let's say when x equals to 0, basically at equilibrium, we know that this whole thing will become 0 because your x is 0. So your Ke will just be 1 over 2m omega square a square. Now this is a bit familiar, isn't it? Look at this. Okay, maybe it's not that familiar because I use a. Okay, let me rewrite this. If I rewrite this as V max equals to plus minus a omega. It's actually the same thing, I just rewrite it. Now, is it familiar? It is, right? So, we can rewrite this better. 1 over 2m a omega square. So, if this whole thing square, we'll get V max square. So that is your kinetic energy when it's maximum. This is the equation for your maximum kinetic energy. Yep. Remember, this one, make sure you open up for both, you know. If you are afraid that you might make the mistake, just stick to this form. Yeah. But yes, you can see it. It's actually maximum velocity. So, I can label this. Okay, let me use a different color. This is 1 over 2 m omega square a square. Okay. And that is my kinetic energy when it's maximum kinetic energy. Okay, so that's about it for our kinetic energy graph. Now how about our potential energy graph? So, our potential energy graph will look something like this. Okay, let's change the color. Okay, let's take this. It will look something like this. As the kinetic energy increases, we know the potential energy will decrease. Right? And we know at equilibrium, when the kinetic energy is maximum, your potential energy is 0. So your graph will be the upside down of your kinetic energy. It will look like this. Yep. And remember to label your graph. This is potential energy. Especially when you have more than one graph, you have to label. This is your kinetic energy. And total energy is 0. Not 0. Total energy is constant. Oh my god, why did I say 0? Total energy is constant. Because it just converts between PE and kinetic energy. But the both of them, when you add, because energy cannot be destroyed, cannot be basically, destroy it. So the only way and the best way, based on energy conversion, your total energy has to be constant, not 0. I don't know why I said 0. Has to be constant. So your total energy, I'm going to put as ET equals to KE plus PE. Yeah, there you go. So we have equation for KE. Is there a way we can have equation for PE as well? Yeah, sure. So we know PE of a spring, ideally, 1 over 2, or because it's elastic potential energy, right? You can have 1 over 2 kx squared. Right. So, and we have learned before that omega equals to sub k over m. So omega square is k over m. If we want to make k as the subject, omega square m equals to k. If let's say the question did not give you a spring constant, you can use this. Or if let's say the question is not about spring, it's about a pendulum. You don't have a spring constant in that case, right? You can use this formula. 1 over 2 m omega square x square. That is your potential energy. So you have your kinetic energy equation and potential energy. Let's find our total energy equation. Okay. E total equals to KE plus PE. Your KE is this. Do not take this yet, because this is maximum KE. We want the KE as a whole, the equation that we derive. So it's 1 over 2 m omega square a square minus 1 over 2 m omega square x square plus your PE is this m omega square x square. These two clearly can cancel out, right? So what you'll get, 1 over 2 m omega square a square. Now is this familiar? Yes, it is very, 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 very familiar. Look at this. It's the same thing. And does it make sense? Yes, because I said that the energy is constant, and you see where the part that it is constant, the value here is the same as my maximum kinetic energy, the value. So that is why you get the same exact formula as your maximum kinetic energy. Okay. Yep. So also another thing to note, realize that this is also, let me use a different color. This is a positive quadratic graph. This whole thing will be constant, definitely, right? And x square is a positive quadratic graph, and you do get a positive quadratic graph for your potential energy. Well, that makes sense? Yeah. So that's about it, about energy in general, how energy changes, the interchange them, and remember total energy is constant, not 0. Okay, it's not 0. God knows why I said 0. It's not 0, it's constant, because energy cannot be destroyed. You just have to interchange between them. You either convert between KE or PE, or PE to KE in this case. So this is our graph of energy against displacement x, and these are some equations that you might want to know. Actually, the other way to derive kinetic energy equation is, instead of putting this formula, right, this one inside here, you can actually put in the cosine and sine form. Remember you got learn a cos omega t, that equation, right? You can put that inside here and you can also derive that. Yeah, you can do that way as well. It's just this way I showed is just another way to do it. That way is also possible. Yeah, so that's about it. Oh, one more thing. We have talked about energy against displacement. Is there a graph for energy against time? Yes, there is. So it's actually a very simple graph. Time. Okay. So your graph would actually look like this. I'm going to draw the graph first, then explain the mechanism behind it. Okay? So okay, it did not touch 0, but okay. Never mind, I think I should just draw it again. Supposed to be touching 0. Then the other graph looks something like this. I should use a different color. This is your PE. And the orange is your KE. And of course, total energy is constant. Very, very constant. So, this is your total energy. PE plus KE. E total. Okay, now, why does it look like that? Okay, I'm going to draw a line in between to show one complete cycle. So you realize, for a simple harmonic motion, both kinetic energy and potential energy go through two complete cycles during one period of oscillation. It has to go through this here. It's actually this is where the T is. It has to go through two complete oscillation. Why? Okay, I think I best show it maybe in pendulum, since I never showed pendulum before. So I just show pendulum. This is your pendulum, and this is perhaps your equilibrium. Then when it swings, it's going to swing here. Then maybe it swing here. So, okay, let me draw. Okay. Alright. So initially it was at equilibrium. So at equilibrium, we know our kinetic energy is maximum. You see here, your kinetic energy is maximum and your potential energy is 0. Right? Then it swings to the maximum amplitude. What happens at maximum amplitude? Your kinetic energy becomes 0. Your potential energy will go up to the maximum. Then it's going to oscillate this way. When it oscillates back this way, it's going to pass through the equilibrium position again. That is why your velocity spikes up to the maximum, potential energy go down. Then when it goes here, potential energy maximum, kinetic energy goes down. Then back to its original position, one complete oscillation. Equilibrium back, kinetic energy go up, potential energy go down. Because for one complete oscillation, when you swing the pendulum, so from here, from equilibrium, it's going to go here, here, then come back. There is one complete oscillation, right? Yep. That is why your graph looks like this. For one period of oscillation, it has to go 2 cycles. The graph is like 2-cycle graph. Yeah. For one complete oscillation. So this is energy time graph. Simple, right? Yeah. So I think we have covered the most of it of energy, and as well as we have covered all the types of graph possibly asked in simple harmonic motion. In the next part, which is not the next video, basically the next part in the same video, I'm going to show you an overview of all the graphs that we have learned. Okay, so this is basically all the graphs that we have learned. And for information, this is from Geogebra. I will put the link down below in the description if you're interested to, play around with it. So now this particle is at equilibrium at the moment, which basically means that x equals to 0. So your displacement graph, x is also equal to 0. And remember, at equilibrium, your velocity is maximum. That's why your velocity is maximum here. This is velocity against displacement graph. Remember our egg, right? And this is velocity against time. Because when you differentiate sine, you're going to get a cosine graph, right? Yep. So this is velocity at maximum as well. And this is acceleration against displacement graph. Since acceleration is directly proportional to displacement, and when x is 0, the acceleration is also 0. And this is acceleration against time graph. You differentiate a cosine graph, you're going to get a negative sine graph. Remember? Yep. And this is what we have learned today. Energy graph. Energy against displacement graph. At displacement, when displacement is equals to 0, basically when x equals to 0, you're at equilibrium, your kinetic energy is maximum. The orange graph is kinetic energy. Kinetic energy is maximum. At equilibrium, your potential energy is 0. Same goes to our energy against time graph. At equilibrium, kinetic energy is maximum and potential energy is 0. So you can actually play around with it to see how the particle moves around the graphs. And it's really pretty cool, you know, when you see it, how it works. And yep, that's about it for today's video. We have done our energy graphs and look at the simple harmonic graph as a whole. I hope you enjoyed this video. I hope you learned something new. Thank you for watching. Thank you for your time. And I'll see you in the next one. Bye bye.